Ever heard this phrase, black holes have no hair? It's actually a fascinating concept in physics called the no-hair theorem. Let's break it down. The no-hair theorem suggests that black holes can be described by just three observable properties: mass, electric charge, and angular momentum. Everything else about the black hole, all the other characteristics, vanish behind the event horizon, the point of no return. Imagine if your personality could only be defined by your weight, your electric charge, and how fast you spin. Weird, right? But that's exactly what happens with black holes. These three parameters are like an ID card for a black hole. Once a black hole forms, all the extra details, or hair, disappear. Physicist John Archibald Wheeler is credited with popularizing the phrase, black holes have no hair. However, it was actually his graduate student, Jacob Bekenstein, who first coined it. And as much as physicist Richard Feynman hated the phrase, it stuck. So why is this important? Well, it tells us that black holes are incredibly simple objects. No matter what goes into a black hole, all that complexity gets erased. All you're left with are these three measurable traits. The first step in proving this idea came in 1967, courtesy of Werner Israel. He showed it for non-rotating black holes. Quickly, the theorem was extended to those that are charged and spinning, but here's the kicker. Even today, there isn't a complete mathematical proof for all types of black holes. It's more of a conjecture, a hypothesis. Stephen Hawking, Brandon Carter, and David C. Robinson made significant strides, but the no-hair theorem remains a partially solved puzzle. Nevertheless, the idea still holds strong. Black holes are uniquely characterized by just mass, charge, and angular momentum. In a way, this simplicity is beautiful. Let's take our understanding a step further with an example. Imagine two black holes with identical masses, electrical charges, and angular momenta. Seems straightforward, right? But here's the twist. One black hole was formed by collapsing ordinary matter, while the other was created from antimatter. You might think they would be fundamentally different. After all, ordinary matter and antimatter are like cosmic opposites. But according to the no-hair theorem, these two black holes would be completely indistinguishable to an observer outside the event horizon. That's right. Despite their wildly different origins, the black holes would appear the same. The special particle physics pseudocharges, like baryonic number or leptonic number, which differ for matter and antimatter, would not be conserved in the black hole. Even if they are somehow conserved, their values would be unobservable from the outside. This concept underscores the profound simplicity and mystery of black holes. No matter what kind of matter they originate from, once formed, they shed all those unique characteristics. All that remains are the core properties: mass, charge, and angular momentum. Let's shift our focus to another intriguing aspect: changing the reference frame. Imagine we have an isolated, unstable black hole. Over time, this black hole decays rapidly, transitioning into a stable state. Except for quantum fluctuations, a stable black hole can be entirely described in a Cartesian coordinate system by 11 key numbers. These numbers include mass energy, electric charge, 3 components of position x, 3 components of linear momentum p, and 3 components of angular momentum j. These 11 numbers represent the conserved attributes of a black hole, which we can determine from a distance by examining its gravitational and electromagnetic fields. Interestingly, all other variations in the black hole will either escape to infinity or be swallowed up by the black hole itself. Here's where it gets fascinating. By changing the reference frame, we can simplify this complex description. We can set the linear momentum and position to 0 and align the spin angular momentum along the positive z-axis. This effectively eliminates 8 of the 11 numbers, leaving us with just 3 that are independent of the reference frame: mass, the magnitude of angular momentum, and electric charge. Therefore, any black hole that has been isolated for a significant period can be described by the Kerr-Newman metric in an appropriately chosen reference frame. This profound simplification underscores the elegance of the universe's natural law. In our previous discussions, we've simplified the understanding of black holes down to a few fundamental properties. However, the no-hair theorem, which underpins much of this understanding, has fascinating extensions that expand its reach and implications. Originally formulated for black holes within the context of a four-dimensional space-time, the no-hair theorem adheres to the Einstein field equation of general relativity with a zero cosmological constant. This setup assumes the presence of electromagnetic fields and optionally other fields such as scalar fields and massive vector fields, also known as Proctor fields. Recent observations have suggested that the cosmological constant might not be zero but positive. This has led to extensions of the no-hair theorem to include scenarios where the cosmological constant is indeed positive. Such extensions are crucial as they align with our evolving understanding of the universe's accelerating expansion. Moreover, some theoretical frameworks predict the existence of magnetic charge. If magnetic monopoles were to be detected, they would introduce a fourth parameter to the description of classical black holes. This parameter would add a new layer of complexity and elegance to our understanding of these enigmatic objects. While the no-hair theorem provides a remarkably streamlined way to understand black holes, it's important to acknowledge that this theorem, like any scientific theory, has its limitations and exceptions. Counterexamples to the no-hair theorem exist, particularly in space-time dimensions higher than 4. Additionally, when non-abelian Yang-Mills fields, non-abelian Proctor fields, some non-minimally coupled scalar fields, or sky-Armians are present, the theorem can fail to hold. These exceptions, however, are often unstable solutions and may not result in conserved quantum numbers, maintaining the spirit of the no-hair conjecture. Some researchers have proposed that hairy black holes could be viewed as bound states of hairless black holes and solitons, adding a layer of complexity to our understanding. In 2004, an exact analytical solution for a 3+1 dimensional spherically symmetric black hole with a minimally coupled self-interacting scalar field was derived. This groundbreaking work showed that black holes could carry a finite scalar charge, in addition to mass, electrical charge, and angular momentum. This scalar charge might result from interaction with cosmological scalar fields such as the inflaton. Although this solution is stable and does not possess any unphysical properties, the existence of a scalar field with the desired characteristics remains speculative. The results from the first observation of gravitational waves in 2015 provide some experimental evidence consistent with the uniqueness of the no-hair theorem. This monumental discovery came from the Laser Interferometer Gravitational Wave Observatory, or LIGO, which detected ripples in space-time caused by the collision of two black holes. The gravitational waves carried information about the masses and spins of the black holes involved, aligning remarkably well with predictions made by the no-hair theorem. This observation is consistent with Stephen Hawking's theoretical work on black holes in the 1970s. Hawking's groundbreaking work laid the foundation for our current understanding of black holes, including the concept that black holes can be characterized entirely by their mass, charge, and angular momentum.